But another change with this session is that these sessions will be recorded, and then they will be edited and they will be posted to YouTube. Um, so that's one of the reasons that microphones have to be off the entire time for everyone, except for me, really, because it's just a privacy issue. We don't want you guys to have to be in a YouTube video without your permission. If we wanted to post it with audio, we would need permission from pretty much every single student in the class. So unfortunately, we can't do it that way. But what's cool about these sessions is although we do lose the microphone interaction, which I know I'm sure a lot of you guys appreciate a lot, because I do, especially when you guys are willing to speak. An advantage of this is that this video is going to be edited down, and then it's also going to be posted to YouTube. So like I said before, you're going to have access to it. Let's just say the day before before midterm, you're starting to brush up on your studying. You can refer back to this video, see how we did certain problems. I know I usually send out the documents for the SI sessions, but this way you don't need that. You can actually refer back to the video. You can see it step by step. And part of that fact that it's going to be posted to YouTube, these sessions are going to be a little bit more towards me showing you how I would do the problem myself. So I'm still going to ask you guys to send your answers. But in the usual session, I might break a question down into a bunch of steps, right? For this session, I'm probably going to ask to see if you can get the answer to the question on your own. And then once we get a couple answers, or maybe, if you guys are having trouble and you can't, I'm just going to go without asking questions in between. I'm just going to straight up show how I would do the question. So it's rather more than you guys practicing. You guys get to watch me do it. And the reason for that is when you post a video to YouTube, let's say you're watching Khan Academy or something, it's not like he's saying, oh, pause the video and work on this, or pause the video and work on this. It's just showing you really how to do it. It's something that you can refer to in the future. So hopefully that's going to be a big advantage. Again, we're going to have these once every other week, every Sunday at 12. I might change it. I might change the day if people, Sunday's a little bit tough day. I understand for people to make it. I could, so this might be up to change for now. For now, it'll be on Sundays. I might check and see, maybe we can move it to Friday or Saturday if it's easier for people. But yeah, that is the difference between alternative virtual SI and the regular virtual SI sessions that we have online. So just to summarize, the big points about this is: 1, microphones and cameras off the entire time other than me. 2, it's not very much a step-by-step process and like a collective effort like the SI session is. And 3, it's going to be edited, posted to YouTube. And 4, I'm going to show pretty much exactly how I would do the problem. So are there any questions about that before I move on? And again, if you do have any questions, please use the chat to ask rather than turning on your microphone. Okay, doesn't seem like there's any questions. I appreciate you guys coming. I know it was short notice, and the notification didn't get to your phone, and then it took a while for the Canvas notification to get pushed out. But I still appreciate the fact that everyone was able to come. Okay, so let's get started. So I know you guys just had a midterm, and I hope you all did well on the midterm. Hopefully it was really similar to the practice exam, and you guys all had a chance to do well, and it was just it was a good experience overall. But what I thought I would do is, since there's no new material to cover, I thought we could do some review questions from kinematics and some forces problems, unlike that we've done in the regular SI sessions. So when finals time comes around, you have something to refer back to, some YouTube videos you can watch that directly correlate to your class, and then you could use those as some type of review. So hopefully that sounds good. Again, any questions, please ask them in the chat. All right, so the first question, you guys have done something similar like this in class. I remember pretty explicitly almost this exact same question being shown to you, but I still think it's a really good idea to understand. And if you understand this, it'll really make sure, as far as all kinematics, you have a really good fundamental understanding of why things are a certain way and why you're getting certain answers. And, maybe, again, on a midterm, you can never just check your answer online or something, or you can't check a solution. So this might help you connect your answer to the question. And, it's kind of a second check, like, okay, maybe the answer is not completely right, but it probably is, because based off, these certain criterias, it matches up with the question. And so the point of this question is, so find the maximum height h and the horizontal range r you can ignore the figure, of a projectile launched with a speed of v naught and initial angle of alpha naught between 0 and 90 degrees. So for a given initial velocity, what is the value of the angle? What value of alpha naught gives the maximum potential height? So what gives the maximum horizontal range as well? So basically, you're asking at what angle is it most ideal to launch a projectile at? And you guys might know the answer, like kind of, I don't want to say intuitively, because you can kind of think about it. But I kind of want to show how we would prove that mathematically. So you guys have the question. Ignore the figure. It's just going to be some regular projectile motion question, so you don't really have to focus on that so much. If we were to draw one, it would just be a simple, say a person standing on the ground and they're just throwing a ball and it has some v naught, and this is some alpha naught that this angle is at. And so this is its projectile. So you're basically looking for this range R, okay, and you're looking for this height H, the maximum height, its peak height. So go ahead, again, like I mentioned before, rather than going through sine of that angle. So pretty much the value that the angle would change or manipulate in the question is all about the value of the angle itself. And so if we think about sine and cosine, we know that both sine and cosine have to be between 0 and 1. So some sine of, we're going to call it alpha because that's what it's called in the question, has to be less than or equal to 1 or greater than or equal to 0. And same thing for cosine, right? I know, I'm sorry, those might look like 2s, but these are alphas. So we know that our maximum value was 1. And so I can already tell just from my knowledge of trig and algebra that our angle has to make the sine of that angle equal to 1. And we're going to get into how we can prove that. So we have certain formulas given by kinematics, right? So we have v sub y is equal to v naught y. V naught y minus gt, because we're dealing with projectile motion. Well, the standard formula for this is plus at. This would equate out to vy is equal to v naught y minus gt for projectile motion, because again, g is negative. And so, acceleration due to gravity would pull something downward, so negative gt. But for this specific question, we're looking for the angle at the maximum height. And we know when something reaches its maximum height, at that exact point, its velocity in the y direction is 0. So we know at this point, v sub y is equal to 0. So that means v naught y minus gt is equal to 0, which is basically saying v naught y is equal to gt, right? So we can tell that the initial velocity at a certain point, or a maximum height, or a maximum point in the y direction, is equal to gravity times time. And would that make sense? Well, we know gravity is meters per second squared. If you multiply that by seconds, you get meters per second. It would make sense. The units line up, velocities in meters per second. So v naught y is equal to gt. Well, we know that t now is equal to v naught y over g. Okay, so we have some formula for time at a certain initial y velocity divided by g. We know that this is true. Well, we need somehow to get our sine into this formula, because right now we don't have much. We have v naught y over g, so there's not much going on as far as being able to solve for theta. But we know that v naught y is also, let me write that over to the side, v naught y is equal to v naught times sine of the angle, which in this case is alpha. So, this is just an identity. We know this, and we can prove this using triangles. V naught sine alpha naught is same thing as v naught y. Well, we can plug that back into our formula for t. So we know that V naught is equal, or T is equal to V naught times sine of alpha naught over G, okay? So we have something for time. And the reason that we did this for time is that we can now plug this into one of our other kinematic equations, which is going to be y is equal to y naught plus v naught y times t plus 1/2 at squared. Like always, we're dealing with projectile motion. So our y naught goes to 0, and our 1/2 at squared becomes negative gt squared. So y is equal to v naught y times t minus 1/2 gt squared. What we can do from here is we can just start plugging in values for our t. At that point, it's going to be able to give us a chance to solve for our alpha naught. And so what we're going to do is y is equal to v naught y times t. We know t is equal to v naught sine alpha naught over g. So plugging that in, we get v naught sine alpha naught over g. And then similarly for the other side, let me just shift some stuff over. Similarly for the other side, we get minus 1/2 g v naught sine alpha naught over g squared. Plugging in more stuff, we get y is equal to v naught sine of alpha naught. And we're getting this from this v naught y over here, because again, we know what v naught y, we know v naught y is equal to v naught sine alpha naught. Okay, so that's the wrong color. V naught sine alpha naught over g. Let me move this over. Minus 1/2, same thing as before, g v naught sine alpha naught squared. Okay, so we have some formula for the y direction. But at this point, we have, what looks like a ton of variables. But if we really think about it, what we're looking at right now is hugely dependent on our sine alpha naught. But we can still simplify a little bit more. So if we were to simplify this, we're going to be left with y is equal to v naught squared sine squared alpha naught for this specific problem over 2g. And the reason that it's going to be like this is that we can see that this is, so these, one of these g's will cancel out with what would have been this g squared. So that would be canceled out. So let me write it out just to make it a little bit easier to understand. So if I was to write this one out, I could see that this was going to be v naught sine alpha naught squared, because you have to multiply this part with this part. So you're left, they're the same thing, v naught sine alpha naught squared over g. Subtract that from 1/2. Again, this g gets canceled out with what would have been this g squared. So minus 1/2, and then this top part of the fraction also has to be squared. V naught sine theta. So v naught squared, I forgot to square these. Sine squared alpha naught over g. If we look at these two, this stuff in the parentheses here is the same as this, except there's a 1/2. So you could think of this as 1 minus 1/2 because they're the same thing. So you end up with y is equal to v naught squared sine squared of alpha naught over 2g. So hopefully that's clear on how I got this part. Well, I can see here that I know that the maximum value of sine is 1, or the maximum value of sine of any angle is 1. So I can tell here that if I want y to be as great as possible, I need the top half of the fraction to be as great as possible, because I can't affect anything here. 2g G is constant. G will never change, on Earth at least. 2, that's just a constant number. V naught squared, again, is something that's given as part of the problem. We're asked to find what the largest angle is possible, or what angle will give us the largest value possible. And if I refer back to my unit circle, right? Okay. I know that at sine is equal to 1 when alpha is 90 degrees. So for the y direction, I could get the greatest y value when hold up, let me erase this unit circle, give myself a little bit more room. So yeah, so v naught squared sine squared alpha naught over 2g. So at that point, if I want to solve for my angle, I'm going to be left with sine of alpha naught is equal to 1, which is my greatest value, when often alpha naught is 90 degrees. So again, 90 degrees would be the greatest value for our y direction if we want that. So this is just for the y direction. So for y is greatest at alpha naught is equal to 90 degrees. Well, that's not our final answer though, right? Because if we're back to the question, we still need to get a value for our horizontal range. Okay. So we can do that now. So yeah, our y value would be greatest at 90 degrees. But for our x, oops, let me insert one more page. We still have another thing to do after this. Right, for our x, we need to do something really similar. So if we refer back to our other question, we already solved for t. So t is equal to v naught, or I'm sorry, it's equal to, yeah, v naught sine alpha naught over g. Sine alpha naught over g. Well, now we're worried about when it hits the ground. Well, if something's at its max height at t, so that's half the distance it traveled, right? Because if I have a projectile, it reaches its maximum height halfway through its travel distance, right? We can kind of tell that implicitly just from projectile motion. So that means it hits the ground at 2t. If this is t, then it hits the ground at 2t because it's another half that it traveled. So 2t is when something hits the ground. Well, I'm just going to multiply it times 2, and I'm going to call that t sub 2 is equal to, this is t sub 2, and this point would be t sub 1. T sub 2 is v naught sine alpha naught over g. Okay, so we have something that we can now plug into our formula for r, or x. So r is equal to, our range is equal to x naught plus v naught x times t plus 1/2 at squared. Well, we know for projectile motion, acceleration is always 0 for x, and we know that it started at some value of 0. That's what we denoted it as. So we know r is equal to v naught x times t. This is equal to v naught cosine of the angle alpha times t, or t sub 2, I'm sorry, which is 2 times v naught of sine alpha naught over g. So this is what our range is equal to. Well, again, we're looking for our max range, right? So now if we start multiplying things from this, so we can consolidate and try to solve for some angle, we know that, so v naught times v naught will give us v naught squared. We need the 2 because it's multiplied by 2, so we're going to put that 2 in the front. So 2 v naught squared. Well, going back to our trig identities, if you remember, cosine of some angle times sine of some angle is equal to sine times 2 of that angle. So it would be sine 2 alpha naught. So you're going to have to brush up on your trig identities for this type of question, right? Because I know that cosine alpha naught times sine alpha naught, based off my trig identities, is the same thing as sine 2 alpha naught. So I'm going to plug that into my formula. And this is all over G. Okay, and again, just like last time, our R is greatest when alpha naught will let sine be 1. Well, it's 2 times alpha naught. So we know sine is greatest at 90. So if sine is greatest at 90, right? And we need to really just divide that by 2. So our max is at 90 degrees, right? We know that this has to equal 90 because we want sine to be 1, sine would be equal at 90. So we know that this would be kind of equal to 90. That's what we're going to say, because in reality it is if we're looking for that max height. So 90 is equal to 2 times alpha, divide each side by 2. Alpha naught is equal to 45 degrees for that. So this gives us the maximum range for any initial speed. Alpha naught is equal to 45 degrees. Okay, and so you might say, hey, we solved for 90 earlier in the question, but all that 90 did really was allow us to solve for that range in the x direction. Because when you really think about it, when you're trying to launch something as far as possible, you're trying to really launch it as far as possible in the x direction. So what this 90 degrees did from this part of the formula, or this part of the question, I'm sorry, it helped us solve for what would actually solve the range. So in general, when you're doing something projectile motion and you're on the ground and you want to throw a baseball, you want to throw it at 45 degrees to get it as far as possible. And I know we went over this in class, but this is something, a video that you can refer back to since lectures aren't recorded. So hopefully in the future, you'll be able to refer to this. So are there any questions? And please remember, if you do have any questions, please put them in the chat. Is there anything confusing about what I described? I can go back to the other page, but this is as most I can zoom out if you need stuff from before. Do you need things from the first page? Like over here. So for this question, it's going to be about forces. So for this specific question, we have, it's a situation, your firm needs to haul granite blocks up a 15-degree slope out of a quarry and lower the dirt into the quarry to fill the holes. You design a system in which a granite block on a cart with steel wheels, weight 1, including both block and cart, is pulled uphill on steel rails by a dirt-filled bucket, weight 2, including both dirt and I think it got cut off a little bit, but that's not too big a deal, including both the dirt and the cart. So that's pretty much the entire question. So this is our system design, and what we're going to be asked to look for or solve for in this specific question, we're going to be asked to find what tension, or I'm sorry, not tension, what weight how much is the weight of both being pulled uphill, the bucket and the cart on the steel rails. So let me write that down. For some reason, I forgot to include that part in the question. So what we're looking for, pull it up real quick, the actual question. Sorry, for some reason it got cut off when I imported it into my notebook. Hang tight for 1 second. I'll pull up the original. Okay, so what we're going to be asked to find is, let me move some stuff out the way. So how must the weights W sub 1 and W sub 2 be related in order for the system to move with constant speed? So I'll explain what that means in a quick second. And then, of course, for these type of questions, we haven't discussed friction yet, so we're just going to skip friction. In order for the system to move with constant speed. So I'm going to explain how we would think about this in a quick second. Okay, so basically what it's asking is if we have some weight 1 and weight 2, right, that we're going to solve for, or not solve for, but, you know, theoretically we're not given actual values for this question. We're kind of just more dealing with variables. What does the ratio of them have to be in order for this thing to have constant speed? And if we think about it, what constant speed really means is no acceleration. And if something has no acceleration, then it has no net force. That's really the core idea of this question. So assuming this thing has no net force and no acceleration, what could we need to somehow solve for a number that will relate W1 and W2? So I know that's a little weird, but pretty much what our answer is going to look like is going to be W2 is equal to some number times W1. So what is X really that's relating? Counteracting tension, which would be this kind of imaginary, is the same thing as this component right here, which is the same thing as W1 sine 15. So I have enough to come up with some formulas now. Let me clear that up a little bit. 15. So now I have some things to come up with some formulas. Well, I know F is equal to ma, but again, this system is moving with constant speed. Constant speed means zero acceleration. Zero acceleration means zero force. So I know the sum of F for the bucket in the y direction is equal to the tension minus the weight, because the weight is counteracting it. So W sub 2. And again, it's not accelerating, so that's just equal to 0. So I know T is equal to W2. So that's how I'm going to relate the cart in the bucket. And then I have F sub X from the cart. That's going to be equal to T. Well, I'm worried about it only in the X direction, right? Because it's not moving in the Y direction as I've defined it. It's only moving in the X direction. T minus W1 times sine of 15, because that is what's counteracting the tension. And again, constant motion or constant velocity, so I know it's equal to 0. So I know T is equal to the weight 1 times sine 15 degrees. So I can now set these two equal to each other because T is the same in both systems. So I know that W2 is equal to W1 times sine of 15. And so I know that the relationship between them is that the weight of the bucket and the cart is going to be equal to the weight of the cart times sine of 15. And I know sine of 15, is everyone able to see my screen now? Did it pause again? We're good? All right, cool. We'll just cut this part out. So hopefully it'll be a lot smoother. So hopefully you guys can see the work that I've done. So if in the y direction, T minus W2 is equal to 0, so that means T is equal to W2. In the x direction, T minus W1 sine of 15 is 0. T is equal to W1 sine of 15. And so T is the same in each system, so I can just equate them. So I know sine of 15 is equal to 0.2588. I'm going to call that 0.26 just because I have 15 2 sig figs. It's just easier to call it that way. I'm just going to round. So that means W2, the relationship between this is that W2 will always be 0.26 times weight 1. And that is my answer.